It's sort of important to me personally because I grew up in Northern Ontario, I went to the University of Waterloo, and then I kind of got exported to the States, and I think I lost my accent, except for the Z, which confuses my students. And yeah, so it just means a lot to me. I should also say a great big thank you to all of my mentors and collaborators over the years who taught me so many things and just made it so much fun to be doing math. We don't do math in a vacuum, so thank you. All right, so today I want to talk about Apollonian circle packings and, if there's a little bit of time, also continued fractions. And the big picture here is that if, as number theorists, we're interested in these Diophantine geometry questions. In this situation, what we're looking at is the orbit of a group. If it were an algebraic group, we'd be in the Diophantine geometry situation. We'd be looking at points on a variety. But we're looking at smaller groups. We're looking at thin groups. And so we don't have the same tools available. But what's interesting is we see a lot of the same sort of phenomena. And so it's interesting to ask why we see some of these sorts of things happening. OK, so I'm going to dive right in with Apollonian circle packing. So take 3 circles and let them have disjoint interiors. So the outer one here, its interior includes infinity. And Apollonius asked a lot of interesting geometric questions about several different objects and how you could put them in relation to one another. And one of the questions was, if you have 3 circles in this arrangement, then how many ways can you add another circle to the 3 that you've got? And there should be 2 solutions. There's these guys. And so what I want to do is add those in. And now we've got 5 circles. We've got new triples for which we can ask the same question and add in more circles. And if we just keep doing this, we get this, this pretty Apollonian gasket. OK, but being number theorists, we can't kind of leave well enough alone. So we're going to add some integers here. So what I've done is I've labeled the circles with their curvatures. So the curvature is 1 over the radius. And so it should be somewhat surprising that in this example here, you see so many integers. All of these circles have radius 1 over an integer. But then it lets you ask the question, why does this happen and what integers do we see? So a theorem of Elizabeth and Descartes answers the question as to why this happens. So let's let A, B, C, and D be 4 mutually tangent circles. So we'll call that a Descartes quadruple. Let's let those be the curvatures. And they showed, and it only uses sort of basic geometry, but it's not very easy, that you have this relationship, this quadratic relationship between the curvatures. So in particular, this reflects Apollonius's observation that if you have 3, there's 2 solutions for the 4th. And so if you have ABC, there's 2, maybe D and D prime, and they satisfy a linear relationship in terms of the previous curvatures. So what this means is that if you get to the point of having 4 integer curvatures, so A, B, C, D, then the D prime will also be an integer. And as you continue, you'll get integers everywhere. So this answers the question why these things exist. So the question that I want to ask is, what are the curvatures that appear? What are the integers? We have a set of integers. What are they? So in order to address the question, we need to take a look at the symmetry group of the packing. So the way that we do that is we organize the packing according to quadruples. So if I have a Descartes quadruple of circles, then there's a swap. So if I fix 3 of them, you can kind of see that they're in red there. If I fix 3 of them, and then that 4th one, I can swap it out for the other solution to that question of Apollonius. And if I do it again, I get back where I started. So in fact, these swaps will generate the entire picture. They'll generate all of the Descartes quadruples that are in the Apollonian circle packing. And you get a free group free product of 4 copies of Z mod 2Z. And because of that linear relationship between the curvatures, so if we think of this group as acting on a vector of 4 curvatures, then the new curvature has this, do this. So it has this relationship to the previous ones. And so you can give a matrix for the swap, which is just going to act on your vector of 4 curvatures to give your new quadruple of curvatures. So we can put this group inside the orthogonal group for that quadratic form that we had earlier. Okay, and that's a 3-1 form. So what's interesting about the Apollonian group is it's far from being that entire orthogonal group. So it's in fact, Zariski dense inside the orthogonal group. But if you look at it as a subgroup of the integer points of that orthogonal group, it's infinite index. So this is what thin group means in this context. And it means that we can't cut out this group by polynomial equations. We don't have the tools that we usually have. Okay, so what we're looking at then is orbits of this group. Now here's a different example of a group orbit that we might want to study. So this is my favorite way of thinking about continued fractions due to Carolyn's series. And what we do here is we break up the real line using the Ferry subdivision. So these are the Ferry fractions. So if you've got 0 and 1 here, I'm going to mark that as sort of being my starting interval with this big arc. And then I'm going to take the mediant between those things. So adding numerator and denominator separately, I get a half, and that gives me 2 subintervals. So by tracking with these arcs, I can sort of explain the iterative subdivision that I'm doing to the real line. And what it does is it gives a sort of addressing system on the real line. So if I'm interested in some number here, say alpha on the real line, I can drop a geodesic down towards that number, and I can kind of read off sort of driving directions, right? I enter one bubble and I go either to the left or the right sub-interval, and then I do that again, okay? And you can formalize this by using, you're generating, when you do this path, you're generating a word in R and L. And if you use these matrices as your R and L matrices, then this formalism right here is actually exactly the same formalism that you're used to for continued fractions. So these guys here, these coefficients of the continued fraction are appearing as the exponents now. Okay, so that means that if I'm interested in some rational number, I'm going to be interested in finite continued fractions, so rational numbers and their continued fraction expansions. And if I'm interested in some particular one, I can think of it as an element of the orbit, say of the vector 0, 1, under maybe some subgroup generated by some words in R and L. All right? So in particular, you might want to look not at all of the rational numbers, but maybe ask questions about rational numbers that have particular features to their continued fraction expansion. So, oh, right, I should have shown you the group here. So if I want to generate using L and R, just making words with positive exponents, so I'm not allowing negative exponents, then I'm sort of generating the semigroup of those things. And that ends up being all of SL2Z, where you allow only non-negative entries. So this is a semigroup. It doesn't have inverses. So everything lives inside here. But you might take a smaller semigroup inside there. So for example, there's a classical conjecture due to Zaremba. And the question is the following. So we're interested in continued fraction expansions that use coefficients only from a specific alphabet. So we're going to use 1, 2, 3, 4, 5 as the allowed coefficients. And we're interested in the rational numbers that have continued fraction expansions of that form. And the question is, if you look at all of those, if you look at that collection, what denominators do you or don't you see? So you're not going to see all rational numbers, but maybe you'll see all denominators. And so Z sub A here is the set of denominators that you will see. So the Q, such that there is some numerator that goes with it, so that the continued fraction expansion can be given in terms of those letters. And the conjecture due to Zaremba is that you do, in fact, get everything if you use the alphabet 1 through 5. In fact, this is a more general question. Is there a finite alphabet for which this will happen? But Zaremba proposed that maybe 5 would do it. And so you can see this also as an orbit. So the idea being that now, if you use these matrices, it turns out that what you're doing is you're controlling the continued fraction expansion to have only coefficients from your particular alphabet. This is going to be some sort of sub-semigroup of this collection of what's generated by R and L. And so you look at this orbit, and these are the rational numbers that you get out, and then you look at what are all the Q's that you collect. Okay, so these are 2 examples of the sorts of problems that we might be interested in. So I should ask if there's questions. No, I really literally just want 1, 2, 3, 4, 5 as the possible coefficients. So in particular, they're bounded. So if you look at the data, 5 seems to do it. So 6 is just even better. Yeah. but 5 does seem to do it. Okay, other questions? Yeah, 4 is missing a few, but it seems to peter out. And you can drop it down and keep doing the data. When you get to 1 and 2, maybe I'll mention this later, we can't go far enough to watch the exceptions disappear, as far as we can tell. All right, so let's go back to the Apollonian circle packing. So let's just sort of build up what are the facts that we know about this set of curvatures. So first off, in this example that I have on the screen, the outer one is curvature 6, but I'll call it -6 because of that interior containing infinity. And so I'm only, all the other ones are going to be positive, so I'm interested just in positive integers. And you'll see that there just isn't room for most of the small integers in this packing, right? There's no way I can fit a 1. I can't even fit a 12 in there once I've got my 11, 14, and 15, okay? So there just isn't enough room to start with. So there's definitely going to be some integers missing. But what happens in the limit? As we go into the limit, we've got lots and lots of corners that we're filling in, right? And so the question is, how many circles are we generating of a given size? And the answer has to do with the Hausdorff dimension of the fractal. So this has nothing to do, this statement right here has nothing to do with an integral packing. It's true for any Apollonian gasket. The Hausdorff dimension is 1.3 something. We now know it to, I think, just recently, 120 something decimal places. I think this is pretty cool. So if we count the number of circles that have curvature below a particular bound, then I'm not, I'm counting with multiplicity if they happen to have repeat curvatures, where I'm just counting circles. Then we have that they grow about x to the 1.305, et cetera, the Hausdorff dimension. So what this means is that there's more circles below the bound x than there are integers below the bound x. So we have to be getting, on average, higher multiplicities for each of the integers if we're in an integral packing. And so in particular, on average, if we're looking at circles that are around size x, the multiplicities should be about x to the 0.3, which is growing. Okay? So we do expect that there's lots of room. So we should maybe at least think we could get all of the integers in the packing. The next thing to do in a room full of number theorists is look at it mod p. So here's the Apollonian circle packing mod 5. And you'll see there are 5 colors, if you're counting. So we see all of the residue classes mod 5. But if you look mod 3, there's only 2 residue classes. So there's, in this example here, there's only 0 and 2 mod 3. It can never be 1 mod 3. So the first task is to explain that. If you go and catalog what can happen in terms of the congruence obstructions, so these modular restrictions of some kind, it turns out that they're all, you can explain all of them mod 24. You don't have to go more than 24. And if you look mod 24, then for any particular integral Apollonian circle packing, it's going to be one of these 6 possibilities for the allowable residue classes mod 24. And so we've just given these a name here. So these are the number of residues in the class, and then the first invertible residue in the list. Okay, it's just some sort of identifying name. Okay. All right, so why does this happen? So here's a picture of an Apollonian circle packing mod 8. So if I start with a Descartes quadruple, so this is the orbit of the quadruples. So if I start with quadruple 7663 and I do swap S4, I end up back with the same quadruple mod 8. In the packing over the integers, of course, I might be moving elsewhere. And so you can see that mod 8, this is finite and it closes up pretty quickly. And we've actually closed up before we managed to hit all of the residue classes mod 8. So we don't see anything 0 mod 8 in this example. Okay? And so this is kind of where the congruence obstructions are coming from. So if we want to analyze that, it actually makes more sense to move the Apollonian group a little bit. We'll take it out of the orthogonal group and put it into PSL2 Z adjoint I. So there's an exceptional isomorphism between PGL2C and SO13 plus. So this is a 3-1 form, so plus is like time preserving in space-time of R. And so up to a finite index thing, which I'm shoving under the rug a little bit, we can put a version of the Apollonian group inside PSL2 Z adjoint I. Okay? And we can think of that then as Mobius transformations that have coefficients in the Gaussian integers. And it's maybe not surprising, Mobius transformations in circles. Okay, so when we're working, now I'm going to drop the P, and you'll forgive me also for that, hopefully. So now that we're working in SL2, we can talk about strong approximation. So the statement of strong approximation, if you say that SL2 has strong approximation, is the statement that if you reduce modulo all different moduli, you end up being surjective. So this is reducing, this is matrices. I'm reducing the entries mod whatever, okay? And I end up, this map is surjective for SL2 all the time. But what about if we have a subgroup inside SL2? Then it may or may not kind of fill out SL2 when you reduce. And in fact, what happens is we say that the Apollonian group has strong approximation. That means that when I reduce A, modulo various different primes here, it is usually SL2. You get the whole thing, okay? But there are finitely many primes where that doesn't happen. So it has strong approximation means there's only finitely many bad primes in this sense. And even the bad ones, in fact, aren't so bad. So you don't get everything in SL2 if you reduce mod 2. If you reduce mod 4, there's some extra stuff missing again. But once you lift far enough, you start getting all the lifts. There's nothing new missing at higher levels. So in fact, what happens is this sort of the bad locus or something for the Apollonian group is 8, that's the power of 2, times 3, which is 24. And so this explains why the congruence obstructions can only exist mod 24. Questions? All right, so this is about the reduction of the group. What about, if we're thinking about an orbit on quadruples, we can actually get a little bit more information somehow by thinking about the orbit, by thinking about maybe the calligraph of the group as we generate using swaps. So we can think about random walks through the Apollonian circle packing. So, so the next sort of tool that goes into studying these things, so the strong approximation was shown by Fuchs. This is due to Varju, the statement that we're gonna build up to here. So the idea is, let's take a look at the calligraph, which means the vertices are the elements of the group, and then I'm gonna have my 4 swaps coming out from each element, right? And so that's a degree 4 graph. If I'm doing it mod something, then it's a finite graph. So on that finite graph, I can imagine putting some mass, distribute mass around on all of the vertices. And then I can imagine a Markov chain, which is gonna let that mass flow. So at every position, it's gonna flow 1/4 of the mass to each of the neighbors, okay? And this is just given by the adjacency matrix. And so you can run this and you can watch the mass distribution that you have stabilize. And what it'll do is it'll stabilize to the uniform distribution. So the uniform distribution is actually an eigenvector for this operator, and the eigenvalue is 1. And then there's some other eigenvalues in the system here. And what happens is that the gap here between these eigenvalues is what controls the rate at which you approach the uniform distribution. So if you have a gap here, then what that's telling you is that that the graph is well mixing. So that if you start at some position and you take a bunch of random walks and you look at the endpoints of those random walks, they're going to be uniformly distributed pretty quickly, like pretty short walks are going to do it. Okay, so this is well mixing. And we have a whole family of calligraphs here because we're looking at the calligraph of the Apollonian group modulo all possible different moduli. And that collection has a sort of persistent gap, okay? And that's what it means to be an expander family. And so this is telling you somehow, just backing off completely philosophically, that, if you look at what's happening mod all these different moduli, that you're seeing just sort of random behavior in all of them pretty quickly. So that if you're up above in the integral Apollonian circle packing, walking around using swaps between your Descartes quadruples, you're probably going to see all different integers up there, okay? All right, so those are some of the tools that go into the analytic methods that we have to approach this problem. Okay, so let me take stock for a second here. So things that we know about the orbit. So there's a sort of definiteness. We're only looking at the positive integers here. The growth rate has to be enough to allow us to ask this question, whether we get everything. We know there can be congruence obstructions. And it's possible, so this group, this Apollonian group, is living inside O31. So there's no obstructions up there that are controlling what's going on. But if there were, then there might be some sort of inherited obstruction as well. All right, so should I ask for questions here? Okay, so the conjecture then, based on all that, is due originally to Graham, Ligarius, Malles, Wilkes, and Jan. So in the early 2000s, there were a series of papers about Apollonian circle packings by those authors. And then refined by Fuchs and Sandin. I'll talk a little bit about the work that they did in a minute. And the conjecture says that if you look at the positive integers, and you take out all of the ones that are restricted by the congruence restrictions, then every sufficiently large thing that's left over should appear somewhere in the packing. So another way to say it is there's finitely many things that you expect, there's finitely many exceptions that are missing. You take out your whole congruence classes, and then everything else should appear. So we should expect to get everything. Now you could phrase this as a counting problem if you wanted. So you could say, let's take a look at the number of integers below bound n that appear as curvatures in the packing. And then what this conjecture is saying is that we get a proportion of n, of all integers, which is either 6 over 24 or 8 over 24, according to how many allowable congruence classes there are, plus a finite error here, finitely many things missing. So what's known so far? So Graham, Ligarius, Malles, Wilkes, and Jan in their original paper, they gave a lower bound of square root n. And then Sarnak wrote a letter to Ligarius, taking an interest in this question, and gave a lower bound of n over square root log n. And then Bourgain and Fuchs were able to show positive density. So this means a lower bound where we have some constant times n, but maybe not necessarily the 6 over 24 or 8 over 24. And then finally, Bourgain and Kantorovich were able to show the correct constant. So this is now the correct constant out here, so the correct main term, and just some power savings over here, okay? And that means density 1 amongst the admissible curvatures in terms of the congruence obstructions. And then there were various generalizations to other classes of packings as well. So, so the main, or one of the biggest tools that's available when you're trying to approach these questions from the analytic number theory side is that there's in fact some subsets of the packing that we do have a better handle on. So if I fix one circle, so let's fix the circle with an 11 here, and I look at the family of things that are tangent to that, so this is shown in blue in the picture, then it turns out that those values are actually values of a quadratic form, or very nearly. So the curvatures in blue here are the values of some integral binary quadratic form translated by that curvature, by 11 here. Okay? And the form itself also has discriminant governed by the 11, minus 4a squared, where a is 11 in the example. And these are also the primitively or properly represented values. So we know a good number of things about values of quadratic forms. And so this is what's been used to approach giving a lower bound. So what you can do is you can collect a bunch of these quadratic forms and try to count all of the things that they represent. And so Bourgain and Fuchs, what they did at the very highest level is an inclusion-exclusion argument. So take a bunch of these quadratic forms, count up all of the things that you know they represent, and then count how much overlap you're seeing. And then you want to sort of give a lower bound on this and an upper bound on that and balance things, and they achieve positive density. And the work of Bourgain and Kantorovich is essentially similar approach. So here there's a sort of more complicated growing region of things. We're going to focus on one integer at a time. So let's say n, and we want to know, is it represented? So this is the characteristic function for being represented by a particular form. And sorry, the notation's changed a little bit. Gamma is my quadratic form now. And so I'm going to take sort of an ensemble of quadratic forms and then a growing region of inputs for those forms and have all that grow carefully according to plan. And then I'm just going to count whether or not n is represented by any of those things. And if you can show that this is positive, then we know that n is represented in the packing. And so these arguments come down to Hardy-Littlewood circle method. Okay, so let's turn to the computational evidence for the conjecture. So yeah, I hear a couple giggles. So this is the bug-eye packing. This picture is taken from the paper of Fuchs and Sandin. And it's that first one there, -1223. And then they took another packing that you can see up there with a -11. And they ran the data for these packings. They computed all of the curvatures up to size 10 to the 8. And then they did a clever thing to try to approach this conjecture. So instead of just looking at what's still missing, what they went back to is this statement that the average multiplicity has to be growing. So this is a histogram of multiplicities. So what they did is they took a region, a range of curvatures, and then for each of the curvatures in that range, they computed the multiplicity to which it appears in the packing and added it to the histogram. So the average multiplicity in this particular range right here was around 400. And so that's where the peak is here. And you sort of see a distribution. It looks kind of like, okay, it's behaving, I don't know, maybe kind of like some randomness there. And so this lump, if you choose a different range of curvatures to look at and do this computation in to collect all of your histogram, this lump will move out this way as you choose a farther out range of curvatures, right? Because the average multiplicity is growing with the size of the curvatures. And so it leaves 0 behind. And if there's really 0 here, then that means that now we're not seeing anything missing from the packing. Okay? So this provides some evidence. All right, so we'll call a curvature missing if it's allowed mod 24, but it doesn't show up, okay? And that's where they went up to. That's from the previous slide. And in terms of the actual missing curvatures, for the bug-eye packing, there were no more missing by the time they got up there. There were still a few missing up in that range, at the top range for the other packing. But the other packing, of course, also, it's bigger numbers, so the numbers are getting bigger faster. It might take longer to see the effect, perhaps. Yeah, and so this is where it was left in about 2011. Okay, and so that takes us to last summer. So James Rickards, who's my postdoc, so this is joint work with James Rickards and then with 2 students, Summer Haig and Clyde Kurtzer. And we were working on an RU project, and the idea, sort of RU/G, graduate students as well. And the idea was to turn the question around. So James had written an interesting paper where he turned the question around. Instead of asking, I have a packing, what are the integers in it? The question was, I have an integer, what packings have it, contain it? And so here we were asking the students to take a look at a pair. I'll give you a pair of curvatures and ask you which Apollonian circle packings contain both curvatures together. Not necessarily tangent, or maybe we want to ask tangent. You know, I mean, it was an open question, right? The first thing to do was just to collect some data. So the idea was, first, let's break it up according to the congruence classes mod 24, because that's sort of a confounding variable. Let's get rid of that. So let's pick 2 congruence classes that are allowed together, at least according to the congruence restrictions. They could appear together in a packing. And then what we'll do is we'll take for x-axis and y-axis the values from one congruence class and the values from the other. And for each pair of a point on the x and y-axis, so a pair of curvatures, just check whether or not there's an Apollonian circle packing which contains it. And we'll put a black dot if they somehow repel. There's no packing that contains those 2 together. And we would expect this to be kind of rare. So maybe, we saw that lots of the small curvatures can't appear just because there isn't enough room, and so there should be small numbers missing like this, or small pairs. But we'd expect this to peter out. And in particular, if the local global to conjecture is true, then what you'd expect is that if you look along any line, so fixing one of the curvatures and asking what other curvatures it can occur with, and it's not a congruence obstruction thing, because we've picked congruence classes that are okay, you'd expect the dots to peter out. There should only be finitely many dots, black dots, on any row or column. Remember, a black dot means that those 2 curvatures somehow never occur together in a packing. Okay, so if local global is true, then any row or column should have only finitely many black dots. So here's a typical graph. So this was 0 mod 24 against 12 mod 24, and this is the actual screenshot from the day we were playing with it. And you can see that there's just a few sort of dots up in the corner, and that's it. And this is kind of what we were expecting to see, and then we were going to kind of ask some questions about maybe how many, or if there's anything interesting going on there. And so there's lots of congruence pairs to compare here, and so Summer put together about 100 of these graphs, comparisons, and they all looked pretty much like this, except for a single one. And so this one has these very prominent lines on it. And you can see they're sort of spacing out. This is a zoom up so you can see it a little better, but it's been sampled funny, so it's the original data. So these lines, they're continuing out, but they seem to be spacing out a little bit farther. And so we started looking at them, figuring out exactly what numbers were missing, and it seemed like there really were families that were kind of repelling each other. And they didn't seem to be disappearing. So if this was an honest-to-goodness phenomenon, if this continued, if this data was reflecting reality, then the local to global conjecture would be false. And in fact, it turns out that it is false. So this is how we discovered it this very roundabout way. It turned out that it didn't really, you didn't have to go so far as to find families that repel each other. You can describe families that are actually just missing from a single packing. But I want to give you also an alternate history. So this is a way we could have, but did not discover the failure of local to global. So what you might do if you had just a collection of missing curvatures from running some data is you just take a look at what they are and see if there's any patterns in there, right? And so here's the first 4,000 curvatures, and what I did here is graph the successive differences so that you can squish them down and sort of see if they're spreading out. And the successive differences are getting bigger, so they're definitely sort of becoming more sparse, right? And they look pretty random. I mean, if you look at this, it looks like it's just a little bit of noise, right? And this is the first 4,000 curvatures. But if we zoom out to 10,000, then you see this is where we were before, and the randomness sort of dissipates, and you end up left something which is clearly some kind of family. Because we're taking successive differences and we're ending up with a line here, this is actually coming from families of squares. All right, so we classified all of the possible families that could be missing according to this phenomenon that we discovered. What I'm going to do is I'm going to show you the argument for just the simplest case where all of the complication disappears. So let's take an Apollonian circle packing. Let's take, in particular, this specific one, -3588. And for that particular packing, I'm going to show you that there's no square curvatures anywhere in the packing. So there's a whole family of squares. All the squares are missing. Okay, one important thing about this packing that I'll mention in a minute is this packing never has any curvatures that are 3 mod 4. Okay? All right. Okay, so what we're going to do is we're going to take a look. We're going to use those quadratic forms that are in the packing. So take a particular circle with curvature n, and remember that the circles which are tangent to it are values of a quadratic form, a translated quadratic form. It's translated by n, so it's the values of the form minus n, and it has discriminant minus 4n squared. So that's telling us something about the circle's tangent to my c. And what I'm going to do is I'm going to look at that quadratic form mod n, and then it becomes degenerate because that divides the discriminant. And by a change of variables, by an equivalence, I can make it just look like something times x squared. So this means that, and the minus n translation has disappeared too. So this is really simple. It's just some constant times x squared. And then the observation is to think about the Kronecker symbol, because we're talking about squares, right? So I'll take the Kronecker symbol with n on the bottom, and the observation is that that can't take values 1 and minus 1, because the x squared is irrelevant there, right? It could take 0 if n divides, or is not co-prime to, if x is not co-prime to n, but it can't ever take a 1 and a minus 1. So it really has a value. There's a value sort of associated to this whole family of circles tangent to my circle. So for C, I'll just define some symbol on C which takes value 1 or minus 1 according to that. And to compute the symbol, all you need to do is find one co-prime curvature touching your circle you're interested in and do the Kronecker symbol. Okay? So now we have a Kronecker symbol, or it's telling us something sort of locally at this one circle in the packing. And the observation is that if you get a -1 out of this computation an, then these guys here can't be squares. Okay? So that means that n can't be a square, and a, the thing's coprime tangent to it, can't be square either. So that rules out squares, but only locally at that one circle. Okay, but why does this extend to the whole packing? So let's try to take a step to the next tangent circle. Suppose we have a C1 and a C2, which are touching each other, maybe coprime, non-zero coprime curvatures. Then if I want to compute that symbol, remember, maybe I'll go back for 1 second. All I have to do is find one tangent curvature and do the symbol with respect to my own curvature. So if I want to compute the symbol associated to those two circles, the first one is A over B, and the second one is B over A. And what this means, since we're in a packing where we never have 3 mod 4, so we get the nice version of quadratic reciprocity, is that the symbols have to be the same. So for the first circle, if you have a -1, then the next circle, you still have a -1. So what this does then is it lets us move around the packing, and the lemma that we need is that you can get from any circle in the packing to any other circle in the packing using some path of coprime curvatures. And with that lemma then, this symbol is now a plus or -1 associated to the entire packing and not just to one circle. And so for this guy, let's just compute it. It's -1, so there can't be any squares anywhere. So what we've done is, to associate some sort of new invariant to the packing. There's also a quartic version of this. So we saw that the Apollonian group lives in the Bianchi group, PSL2 Z adjoint I. So it's really, there's something Gaussian going on about everything. And so we actually get quartic reciprocity as well, which rules out 4th power families. And so there's a symbol you can associate 1i -1 or -I, and it will square to the quartic symbol. Right. And so we get all of these different families, which we classify. I want to say just one slide, a little bit about the quartic situation, because it's kind of interesting. So for the quartic reciprocity, you have to have access to the Gaussian integers, and not just the values of the quadratic form, which are integers, right? But a quadratic form, is associated to an ideal class, and these quadratic forms are all coming from ideal classes in the Gaussian integers. So if we can get that underlying ideal class instead of the form, then we can actually evaluate on elements of that lattice, of that ideal lattice, instead of the values of the form. So we use a quartic symbol on elements of the lattice. And the way to get the lattice is to think about the circle that you're taking a look at in a bigger context. So it turns out that if you want to, you can place all of these integral Apollonian circle packings into one single picture. So Graham, Legarius, Malzolz, and Jan drew this picture and called it the Apollonian super packing. And in here, every integral Apollonian circle packing occurs somewhere, okay? And these have a definite location in the complex plane. So in fact, any one of these you can think of as an image of the real line under some Mobius transformation with Gaussian integer entries. This is actually an orbit of the real line under Mobius transformations with Gaussian integer entries. You'll get this picture. And it was studied by Asmus Schmidt. So I sometimes call this a Schmidt arrangement. So if I use the Mobius transformation, the matrix up there, then the lower row is actually what gives me my ideal class. And it's in some sense the lattice of denominators for all of the rational points on that circle. Anyway, I won't go into all of the details of that, but I just wanted to show that because I think it's interesting how you have to access the quartic reciprocity. Okay, so here's the table. So now my types have been augmented with values of the chi2 or chi4 for that packing. I only put the chi4 if it's relevant. And then these are the families that are missing for quadratic families and 4th power families. And you'll see that there's still 2 rows here where there aren't families missing. So up at the top and this guy right here. And for those guys, the local to global conjecture might still be true. But all these other ones have have specific families missing. All right, so we can update the conjecture. So the idea is now we know you could be missing because of congruence restrictions or because of reciprocity obstructions. And so the sporadic set is everything that's missing, but not for a good reason, not for either the reciprocity reason or the congruence reason. And then the conjecture is that for any primitive integral Apollonian circle packing, the sporadic set should be finite. And James did some incredible programming, some very efficient programming. We got up to 10 to the 10, even 10 to the 12 sometimes in terms of the sizes of the curvatures, and computed these sporadic sets. And we took numerous packings from each of the types, and we went until we were 10 times farther than the last missing sporadic curvature without seeing another one. So the data supports it as far as data goes. And now we have, in addition to the list of possible phenomena that you see controlling what integers appear in one of these orbits, we have now this reciprocity. Right, and so what's interesting, I think, is that this is not unlike, I mean, it's called the local global principle or local global conjecture, you know, in analogy to the Diophantine geometry situation where you might have a Hasse principle. And then we find something new coming along, which is breaking that, and it turns out it comes from quadratic reciprocity. So it's reminiscent of a Brouwer-Mannon obstruction, but as far as we can tell, it's certainly not easy to fit it into the same or some sort of analogous framework. In particular, it seems to be supported in some sense on infinitely many primes. And I'd be happy to chat with people about that if people are curious at some point. Okay, so I have another 10 minutes or so. Yeah. So I'll talk a little bit about continued fractions with what's left of the time. So let's go back to the Zaremba conjecture. So here we have a lot of the same phenomena that we had for the Apollonian circle packing situation. So we have a limit set, which is made up of all of the points in the real line that have those continued fraction expansions you're interested in. So that's analogous to the Apollonian gasket, and it has a Hausdorff dimension. And Hensley took a look at these things and showed that the growth rate, the number of things in the orbit, that grows according to the Hausdorff dimension. So this is analogous to what happens in the Apollonian gasket. You've got growth according to the Hausdorff dimension, and it's 2 times the Hausdorff dimension here. So if your Hausdorff dimension is bigger than a half, then you expect the average multiplicity to go to infinity of your, say, denominators. So then Hensley made the conjecture that if you are in that situation, if you have big enough Hausdorff dimension, then the denominator set associated to your alphabet should contain all but finitely many positive integers. And this is now for any finite alphabet, this conjecture. So here's some examples. So Zaremba's conjecture is about 1 through 5. The Hausdorff dimension is about 0.8. As you make your alphabet a little bit smaller, you can see it shrinks. When we have 1, 2, we can take the data quite far computing, but we still see many missing denominators. So it's unclear if they're going to peter out. But Bourgain and Kantorovich made the observation that you can get congruence obstructions. So this conjecture of Hensley's, as it's stated, isn't quite right because it doesn't account for some sort of congruence obstructions. And they showed that with this alphabet, you never see anything which is 3 mod 4. So there is a congruence obstruction possible, and that's analogous to what happens in the Apollonian case. Oh, and I forgot to mention while I had the picture up, let me go back for 1 second and just point something out. So this picture here, this is the analog to that fairy subdivision of the real line that I showed earlier. If you want to do continued fractions with Gaussian integer coefficients instead of approximating real numbers with continued fractions with integer coefficients. So if you want to do continued fractions over the Gaussian integers, this is the picture you draw. And that's what Asmus Schmidt was doing when he was drawing this picture. And so there really is a tighter analogy in some sense. These Apollonian circle packings are not really an arbitrary, like it's not a surprise that arithmetic comes out of these things, because they're actually right there if you try to do some continued fractions in the Gaussian integers. Okay, so yeah, so we're seeing lots of analogies to the Apollonian circle packing case. Okay, so what we saw when I was first explaining about the continued fractions is what we're really studying is orbits of semigroups inside SL2Z greater than or equal to 0. So James and I, so this is joint work with James, this part here, we set out to try to create some sort of reciprocity obstruction in this situation. And so we wanted to preserve the Kronecker symbol in some way as we were walking around the group, okay? And it turns out that it makes sense when you're messing around with this to start looking at this set here. So this is, so I'm gonna first restrict to gamma 1,4. This is, again, I don't want like to deal with 3 mod 4 and stuff like that. So this is to simplify things. It's not clear whether you can get rid of this, but let's go down into gamma 1,4. And then let's take a look at all of the matrices that have Kronecker symbol of their first row equal to 1. It turns out that this is equivalent to Kronecker symbol of first column or second row. You can use any particular one of those. And it turns out that it is a semigroup, and it preserves Kronecker symbol when you multiply. So if you have a vector with Kronecker symbol of first over second of whatever symbol, and then you multiply by something in this group, it preserves that Kronecker symbol, at least assuming that your vector is chosen according to some congruence conditions. There's a few details. And so if you think about it that way, then you can see that it's a semigroup, but it's not obvious, it's not so easy to check this actually. And this has a fascinating consequence in terms of continued fractions, which is that like you can break up the real line. You can think of each rational number on the real line as having a Kronecker symbol, numerator over denominator. And some of them are positive and some of them are Kronecker negative. And then what this is saying is essentially that if you were to take the continued fraction expansion of 2 of these guys and concatenate, then you actually get multiplication of the symbols. Now there's some details, it's not exactly true as stated, but because of the concatenation is like whatever. So, but it's just a fascinating observation to me, very strange. Okay, but so with this we can make an example of what seems to be a reciprocity obstruction. So if we want to give a precise statement here, let x and y be positive coprime integers where y is odd and the symbol is -1. So that's my starting point. And then I'm going to apply the orbit of psi to that, and we'll find that the numerators and denominators can never be squares. And again, the reason this works comes from quadratic reciprocity. And if you want a more specific group, so that psi is sort of large and mysterious, it's not finitely generated, we could take 2 elements of it. We could take this guy, which is finitely generated, has Hausdorff dimension 1.4, and then we could take the orbit on an explicit, let's say 2, 3, and then we will never see squares. But there's no congruence obstruction, so it's not because of that. So we did some data for that. And if you want a statement that's like Zaremba, if you want something that's kind of a continued fraction statement, then here's an example. So let's take all of the rational numbers which are formed from continued fraction expansions where the alphabet I'm using is multiples of 4, between 4 and 128, but with this funny caveat that I'm going to add a 112 at the end. Okay? Then the Hausdorff dimension is bigger than 1/2. There's no congruence obstructions, but no square denominators. So the squares are missing here. And so this doesn't disprove Zaremba's conjecture, because of this, especially because of this 112. But it is a finite alphabet, and it's sort of in the same family of things. And so Bergain and Kantorovich gave various generalizations of this Zaremba-type conjecture, which might include such a thing. Okay, thank you.